Hello dear students, welcome you all. So in this lecture I am going to discuss about the PSK modulation, right? So PSK here stands for phase shift keying. So this is the next digital modulation technique that we are discussing here in this topic of digital communication, right? Earlier we have gone through ASK, amplitude shift keying, and then frequency shift keying modulation techniques, right? So this is the next one, PSK modulation, right? So PSK, as I told you, phase shift keying. Obviously, in this modulation, we are changing the phase of the high frequency carrier wave in accordance with the input bit stream. You can see here, this is the input bit stream or the message signal f of t. You can see here, and first of all, this input bit stream is converted into a bipolar NRZ format. Bipolar NRZ. NRZ stands for non-returning to zero format. Right? You can see here 1 corresponds to +1, 0 corresponds to -1. So this is the NRZ format of this waveform, and this is a high frequency carrier wave, right? And this is the resultant B of T, but it is PSK signal. So you can see here, when the input bit is 1 1, we don't have any change in the phase. The phase is same. But when the bit stream changes from 1 to 0, you can see here there is a phase change of 180 degree, right? So then after when 0 0, no change, right? But when we come to 1 here again, then between 0 and 1 there is a phase change of 180 degree. So again there you have a change in phase. So you can see here. So if I look at the original carrier wave and this resultant PSK wave, then I can see that at those points at which the input bit stream is 0, there is a phase change of 180 degree, and at those points where the input bit stream is 1 1, there is no change in the phase. So this is the PSK modulation, right? I can write this high frequency carrier wave as a B of C T as A cos of vega C T. So in modulation technique, what we have a B PSK T is equal to A cos of vega C T plus theta, right? Now the value of the theta depend upon whether the input bit stream that is carrying the information, it is 1 or 0. If it is 1, theta is equal to 0 for a bit 1, and it is equal to 180 degree if the bit is a 0. So you can see if I put it here, I will get simply A cos of vega t plus 0 means vega t, and A cos of vega t plus 180 degree minus A cos vega t. So the resultant PSK signal, I can call them that signal as plus minus V, not V, A cos of vega C T. This is the resultant BPSK signal, right? That is shown here. So this is the simple understanding of the working of PSK modulation. Now PSK modulation can be further of two broader types, right? Here in this case also we are using only two value of the phase in case of the modulated PSK wave. So it is, we can call binary PSK modulation, BPSK. I can add here PSK modulation. In the coming lecture, we will also learn about or discuss about the quadrature phase shift keying, QPSK, and then M array PSK also, right? So the thing will become more clearer when we will go to the QPSK and M ray PSK modulation. But here BPSK means binary PSK. We are using only two phase angles, either 0 degree or 180 degree for changing the phase of high frequency carrier wave, right? Now, how we can produce BPSK signal? So, for production of BPSK signal, we use a BPSK modulator. It is shown here. You can see BPSK, binary phase shift keying modulator. So, it is having a bipolar and NRZ encoder. It is shown here. The purpose of this using bipolar NRZ encoder is to change this bit stream into bipolar format. As I told you here also, right? Then after this bipolar NRZ signal is mixed with high frequency carrier wave, that is shown here, BCT A cos of vega C T, right? So the one input of product modulator is high frequency carrier wave and the other is this bipolar NRZ signal, right? This is shown here, right? So then after we got this wave that is shown here, that is also shown here. So as far as this particular signal is concerned, here it is 0. So 0 means the phase of the high frequency carrier wave will be inverted by 180 degree, you can see, right? Then after it is 1 means same phase. So from here to here we will have a same phase, no change in the phase. But then after again when we have 0, then again there is a it was from here to here. But again at this point again we have a change of phase. So you can see 0, 1, then 0, 1 in this way. So in this way you will get a resultant waveform of this type, right? In that waveform the change in phase will take place at those points where the input bit is 0 and the phase change will be 180 degree. So this is the simple working of a BPSK modulator. You can see here. So the resultant BPSK modulator signal is represented as a plus minus A cos of vega C T. I show you already here, right? It is written as here, right? So this is the simple way of producing BPSK signals, right? Now the next step is how we can demodulate or detect these BPSK signals. So obviously we are going to make the use of detection for the detection of this wave as synchronous detection method, right? You can see here that we call coherent PSK detection or a coherent PSK demodulation technique, right? We have already gone through the coherent detection methods for the case of ASK and FSK. So we have seen there that in coherent PSK ASK or FSK detection, we need a carrier wave of the same frequency that was used at the modulating station when the modulation was done. So there are two ways of recovering that carrier wave. One is either producing it with the help of a high frequency oscillator that is oscillating at that frequency, and the other method is to extract or remove this carrier wave from the incoming high frequency modulated PSK signal. You can see here, right? This entire box, is a synchronizing circuit, and the task of this circuit is to recover the high frequency carrier wave. That is what that wave will be obviously cos of vega C T. That is this wave that we have taken here, this way, right? So this wave then will be applied to the synchronized detector, that is obviously a multiplier circuit, right? This is low pass filter and this is a comparator, right? So you can see we have applied this signal that is PSK. It is obviously plus minus A cos of vega Ct, one directly to synchronous detector and one to this side to the this square law detector, then band pass filter, and then frequency divider, right? So we will understand how this coherent PSK detection method will detect the PSK modulated signal, right? So let's suppose that the input signal that appear here is plus a cos of vega c t, right? At that time, the output of this square law detector will be a square cos square vega c t, and then after it will be passed through a band pass filter. So the output of this band pass filter that will be a square divided by 2 1 plus cos of 2 into vega c t, right? So then after we can see here that when we will pass this is the output here, this is the output here, right? Square law detector, we are getting this, sorry, I mistaken here. Actually, this is the output of a square law detector. I can write it in this form. A square, it is cos square theta. So I can write it as a cos square theta is 1 by 2 1 plus cos 2 theta. So a square divided by 2 1 plus cos 2 vega c t. Then after it is passed through a band pass filter. So when we pass through band pass filter, but we will get cos of 2 into vega c t, right? Other frequency components will be eliminated. So when now the next task is to half this frequency cos of 2 vega c t. So frequency divider network, when we use through it, we will get finally cos of vega c t. So this is the way of recovering the carrier wave that was used at the time of modulation in this process, right? So one way is that, other way is generating this carrier wave with the help of a local oscillator. This is also the way, right? So then after this is applied to the synchronous detector multiplier circuit. One input to this is a cos of vega ct and the other is a cos of vega ct. So the output is obviously a cos square vega c t. So then after this output is passed to the low pass filter, right? So when we pass it through the low pass filter, a cos square vega ct. Obviously, when we will expand it, it can be expanded into a by 2 plus some harmonics. Harmonics means terms containing different frequencies in terms of cos or sine, right? So this low pass filter will eliminate all these frequencies and it will retain only a by 2. So then after a by 2, this amplitude or this variation is sent to a comparator for encoding it into the form of a bit stream, A to D conversion we can say. So then after we will get what was the bit stream 0, 1, 0, 1, what was the original bit stream that was used here, 0 or 1, it was in fact 1, 0, 1, 0. So whatever it can be, so that can be recovered at here, right? Then after it will be sent for driving the a speaker or a monitor, right, to get the display of that signal. So this is the way of recovering PSK modulated signal, that is phase shift keying modulated signal, and the method used is a coherent PSK detection method, right? So now I am coming to the next step, that is what are the different advantages, disadvantages and applications of PSK modulation that we discussed here. So we can see here the advantages of phase shift keyings include the following, right? This type of phase shift keying allow information to be carried with a radio communication signal more efficiently than FSK and ASK, right? QPSK that I told you in the beginning, quadrature phase shift keying, is another kind of data transmission where 4 phase state instead of 2 right? I told you that in this particular present lecture we discussed only about the two phase values, 0 and 180 degree. But in quadrature phase shift keying that I will discuss in the coming lecture, we will use four phase values, all 90 degree apart from one another, right? So in that case, we can utilize PSK in this format. It is less vulnerable to the fault or errors as compared to the ASK modulation and occupy the similar bandwidth as ASK, right? As far as the data transmission rate is concerned, we can attain high data transfer rate by using quadrature phase shift keying or M array phase shift keying, that is 16 16 or 32 or 64 a quadrature amplitude modulation. This is mentioned here, but we can use it in the case of quadrature phase shift keying also, right? So high data transmission rate can be achieved in this. Now I'm coming to the drawbacks. As far as the various drawbacks or disadvantages of PSK is concerned, the bandwidth efficiency in this PSK is less as compared to ASK. It is non-coherent, reference signal. By estimating the phase states of the signal, the binary information can be decoded. And algorithm recovery in this case is extremely difficult. I mean, the entire process is very complex. We can say in the simple words. Like high level PSK modulation like QPSK 16QM is more sensitive to the phase differences and phase changes that are induced in the communication channel, right? So all these are the drawbacks, right? What are the applications of PSK? Then application, it is broadly used for biometric attendance, wireless LAN, right, along with Bluetooth, RFID, radio frequency identification, optical communication, right, multi-channel, wavelength division multiplexing. This is what here we can use it, WDM, wavelength division multiplexing. So all these are the applications of PSK, right? So this is all about the phase shift keying. So in the coming lecture, we will discuss the another type of PSK, that is quadrature phase shift keying, right? So thank you very much.